Hi students, in this video we're going to talk about valence shell electron pair repulsion theory, otherwise known as VSEPR theory. What VSEPR says is that electrons repel each other, and because they do this, it's going to push the electrons in different bonds or lone pairs as far apart as possible in the molecule, and that's going to give our different molecules different specific shapes. And if we look at BF3, or we could do BH3, either way, what we see is that BH3 is bonded to 3 hydrogens, and so we have 3 single bonds around this central atom. Now, the 2 electrons that make up a single bond, those are stuck together. They can't get apart, but the electrons of one bond and the electrons of another bond are allowed to repel each other, and they do because they're negatively charged. So the electrons in this bond try to get as far apart from the electrons in this bond as they can, and the same with the electrons in that bond, and the same with the electrons in that bond and that bond. And that means that it gives BH3 a specific geometry. Now, the different geometries of our different molecules are going to depend upon how many electron groups we have surrounding the central atom of interest. So, if we have 2 electron groups around our central atom, what's going to happen is that the 2 groups will repel each other and get as far apart as possible. So let's look at BCl2. And again, I'm sorry about the subscript issue, but PowerPoint wasn't letting me show you guys the pictures, so I had to switch over to Notability. And Notability was messing up the subscripts and squishing some of the pictures, but that's okay, we'll deal with it. Now, looking at BCl2, what we notice is beryllium is single bonded on each side to those chlorines. Now, the electrons that make up a single bond, they're stuck together, so we are going to keep them together, but the electrons in this bond and the electrons in this bond, they don't like each other. They're going to repel each other and try to get as far apart as possible to go ahead and minimize that repulsion. And that means that when we have a central atom and 2 electron groups around them, as far apart as possible is 180 degrees. So that means that this molecule's shape right here is linear. So we can see that up here. It's squished, but it says linear geometry. Now, the same thing happens in CO2. We have a central carbon, and it's doubly bonded to an oxygen on each side. Now, there's 2 electrons here and 2 electrons there, so the double bond is made up of 4 electrons. But because they're in a bond, those ones can't get away from each other, but they can repel the double bond or the other 4 electrons on the other side, and they do. And to get as far apart as possible, those 2 electron groups, the 2 double bonds, get 180 degrees from each other, so that gives us another linear molecule. So all of those atoms are lined up straight and they fit into the plane of the board or the plane of the paper or the plane of your screen. So again, that's linear geometry when we have two electron groups around the central atom. Now, what happens when we have three electron groups around the central atom? Well, there's two different ways that we can do this. We can have all of our electron groups as bonds, or we can have bonds and a lone pair of electrons. And those are electron groups, those two bonds, and the lone pair is also an electron group. Now, again, the electrons in a bond are stuck together, and the electrons in the lone pair are stuck together. So the electrons in the bond or in a lone pair can't get apart from each other, but they can repel other electrons that are in other bonds or lone pairs. So what happens is, in order to get as far apart as possible when you have three electron groups around a central atom, is that we end up having a bond angle of approximately 120 degrees. All the way around. So 120, 120, and 120. And this makes the molecule planar, meaning all of the atoms and bonds are in the plane of the board or the paper or your screen. And that is called trigonal planar geometry. It's also called triangular planar in some books, but it's exactly the same thing. Now, there is another way of doing geometry, and one of them is called molecular geometry, and the other one is called electron pair geometry. Now, molecular geometry, what it does is it looks at the geometry of the bonding electrons around the central atom. And electron pair geometry looks at the bonding pairs and the lone pairs around the central atom. Now, if you guys go on to Chem 1A, you'll do both molecular geometry and electron pair geometry. But in 2A, we don't tend to see the electron pair geometry very often, so just keep that in mind. So what we have here is trigonal planar, and over here it'll tell you trigonal planar or bent and angular, and bent and angular is talking about when we have molecular geometry and we're ignoring the lone pairs and only looking at the bonding pairs. But again, you don't tend to see that one in 2A. What you will see is this guy over here with trigonal planar geometry. Now over in the GEF2, you would also have bond angles of approximately 120 degrees. They're slightly different because of that lone pair issue, and lone pairs take up a little bit more room, and we'll talk about that a little bit on the next slide. Okay, so what happens if you have 4 electron groups around your central atom? Now there's 3 different ways we could see this. The first one is if we have a central atom And all of our electron pairs are bonding or are in bonds. So we'll see that right here. All 4 electron pairs are making up 4 single bonds. The other way that we will see 4 electron groups around a central atom is if we have 3 single bonds and we have a lone pair. So again, that is 4 groups of electrons. It's just that one of the groups is a lone pair and 3 of them are single bonds. The third way we will see this is if we have 2 of our electron groups bonding and 2 of our electron groups in lone pairs. So again, we've got a central atom with 4 electron groups around them. Now, if we were to look at CH4, which is methane, you would have a central carbon and it would be bonded by single bonds to 4 hydrogens all the way around. And that geometry is called tetrahedral. That's tetrahedral whether we're talking about molecular geometry or electron pair geometry. But again, in 2A, we tend to talk about molecular geometry and not electron pair geometry. So how these 4 electron groups get as far apart as possible is by having a bond angle of 109.5 degrees all the way around. So you can see that right there. And this one doesn't look like those are 109.5 degrees, but they are. And this one is also. And I will post a video with this molecule made in 3D so you guys can get a better picture of it. So what this looks like is that these 2 bonds right here are in the plane of the screen. So they are flat on the screen, whereas this bond in this hydrogen atom right here is coming out at you, and we notate that with a wedge. And this bond back here that we do a little dashed line on, and that hydrogen back there is pointing back into your screen. So again, the regular straight line bonds, those are in the plane of the screen, and the wedge is coming towards you, and the dashed line is going back in towards the board or back behind the paper or the screen. Now, where do we get the name tetrahedral geometry? Well, it's from the shape of a tetrahedron. So we would have the hydrogens at the points of the tetrahedron, and we would have the carbon in the center, like that. Okay, so what happens if we replace one of the bonding pairs, that one of the single bonds, with a lone pair? Well, then we get tetrahedral or triangular pyramidal. And this is also called trigonal pyramidal. Okay, so in electron pair geometry, you still have 4 electron pairs around the central atom, so that's still called tetrahedral. But again, in 2A, we tend to go with molecular geometry, which just looks at the bonding pairs and ignores the lone pairs. And that's how we get trigonal or triangular pyramidal for this shape right here. And you will see that in chapter 4, at the end of chapter 4 in your textbook. Now, This tells us right here, when we have 3 bonds and 1 lone pair around the central atom, that we have a bond of 107 degrees, a bond angle. And that is a little bit less than 109.5. So we have 107, 107, and this around here doesn't look like it, but it's 107 degrees right there. And the reason for that is because the lone pairs, when they're not bonding to something, when they're just on their own, they tend to puff up and take up a little bit of extra space. So that means they push down on those bonding electrons, and they squish the angle from 109.5 to 107. So again, if we were looking at tetrahedral here, where we have our central atom bonding to 4 atoms, we have bond angles of 109.5 all the way around. And if one of those bonding pairs is replaced by a lone pair, the lone pair puffs up, takes up more room, and squishes the bond angles of 109.5 to that 107. And again, I'll post a little video of this molecule that I make so you can see it in 3D. Now the next example that we have is if we have a central atom that is bonded to 2 other atoms. So we've got 2 bonding pairs and we have 2 lone pairs. Now electron geometry looks at all of the pairs around that central atom bonding and lone pairs. And if you've got 4 electron pairs around your central atom, the shape is still tetrahedral. But again, we don't tend to do electron geometry. We tend to just stick with molecular geometry, which again looks at the molecular shape just based on the bonding electrons. And we ignore the lone pairs, and that gives us a geometry that's called bent or angular, and your Smith textbook calls it bent. Now an example of this is with water. So we have H2O. You guys have seen this before. You have an oxygen that is bonded to 2 hydrogens and it has 2 lone pairs. But that's a basic Lewis structure that we usually draw, but it's not completely correct if we're talking about the molecular geometry of this molecule. So what happens is that we have a structure that we draw like this quite often. And that's showing you that those 2 hydrogens are not 180 degrees apart. They're actually 105 degrees apart. Now the reason it's not 109.5 or 107 is again because of those lone pairs. The first lone pair pushed the bond angle down from 109.5 to 107. But if you add in a second lone pair, that one's going to want to take up a little more room than if it were a bonding pair. And that pushes this bond from 107 down to 105. So that one's 105.9. Now, this example up here was ammonia, NH3. And when we draw the typical Lewis dot structure for ammonia, we usually draw it like that. And that would indicate that we had a couple of 90-degree angles. And right here we had an angle of 180 degrees. But we know now that those angles are not correct. If we draw the correct geometry for this, we will get that we have bond angles of 107 degrees. Okay, so how do we draw this with correct geometry? That's on this slide right here. So say we have the molecule methane. How we would generally draw that with a basic Lewis structure is like this, but that's showing us that we have a bunch of 90-degree angles all the way around, and the molecule looks planar or flat. But now we know that the molecule in real life is not flat. It has a tetrahedral geometry. So when we're drawing a tetrahedral geometry, what we have is we have two of our bonds that are in the plane of the screen. So the hydrogen, the carbon, and the hydrogen right here, those are laying flat on the screen. And then we have one hydrogen that's coming out at us, and we draw that with a wedge. And then we have another hydrogen that's going back into the screen, and we draw that with a dashed line. Now up here it says hatched wedge, but I've never heard anybody call it a hatched wedge before. Most of us just go ahead and draw it with some dashes and don't even bother to draw it in a wedge shape. So that's okay if you just put the dashes like that. And again, I'll put a video that shows this molecule so you guys can see it in real life. Now, if we combine the polarity lesson with geometry, what we get into is molecular polarity. So we took a look at the polarity of certain bonds in the last lecture, and we looked at the bond between hydrogen and chlorine, and we said because chlorine has a lot more electronegativity, it has a higher electronegativity value, that the chlorine would hog the electrons, and that means that they get pulled over towards the chlorine and away from the hydrogen. So we could draw a dipole moment like that, or we could indicate that the chlorine was hogging the electrons, pushing the electron cloud towards itself with the lowercase delta and the minus symbol, creating a partially positive side over by the hydrogen. So we have poles, partially negative and partially positive. But what happens when we have other bonds in our molecule? Well, we have to look at each bond individually. Now, if we're looking at carbon dioxide, what we have is this structure here. And if we draw it with correct geometry, we will see that it's linear. And if we look at the carbon-oxygen bond on the right-hand side, what we would draw is a dipole moment like that because our oxygen is more electronegative than our carbon. And so that oxygen on the right-hand side is trying to pull the electrons toward it. But what happens on the opposite side is you have exactly the same electronegativity value from oxygen on the other side, pulling in exactly the opposite direction. So one oxygen on one side's trying to pull the electron cloud towards it, but on exactly the opposite side, we have an oxygen doing the same thing. So they're directly opposed. So even though it looks like we have two dipoles right there, they're opposing each other with the same strength. So the molecule as a whole has no net dipole. And you can see that right here. So carbon dioxide is a nonpolar molecule. It doesn't have any areas that are partially negative or any areas that are partially positive. Now let's take a look at some other molecules. So BF3, if we were to draw the correct Lewis dot structure for BF3, it would look like this. But we now know that those 90-degree angles that we drew on the bottom and the 180-degree angle that we drew on the top aren't showing us the correct geometry of this molecule. So what we need to do is say, okay, I've got a central atom that is bonded to three different things, so I need to draw it in a trigonal planar geometry because we just learned that. Now if you have trigonal planar geometry, what you're going to have is you're going to have bond angles all the way around that are what? Think of a circle and you're going to divide it into three angles. So you have bond angles of 120 degrees all the way around. Okay, so now that we know that, what we can do is take a look at each of our bonds individually and decide if we have any molecular polarity. So B and F, what we'll have is that fluorine right there will try to pull the electron cloud towards itself. Because fluorine is the most electronegative atom, it has an electronegativity value of 4.0, whereas B is just our 2.0 right there. And this bond up here is doing the same thing. The fluorine's trying to pull the electrons towards itself, and this bond over here, the fluorine is trying to pull the electrons towards itself. Now it doesn't matter which side you write the dipole moments for each bond. So with the bond on the bottom, I could draw it on the right-hand side, or I could draw it on the left-hand side. And with this bond right here, I could draw it under the bond, or I could draw it over the bond. Same with this one right here. It doesn't matter. But what we'll notice is that with the fluorines, when one fluorine is pulling the electrons out towards itself, what you have is two other fluorines pulling back this way. And even though they're both pulling out this way like that, that adds up to opposition this way that directly opposes the electrons being pulled that way. The same thing happens when this fluorine right here tries to pull the electrons towards itself. You have two fluorines on the other side pulling that way, and that adds up to direct opposition to this fluorine over here pulling this way. Now, if you guys go on to do calculus and physics, you'll talk about something called vectors, which makes it a lot easier to talk about the forces pulling the electrons here. So what we find in this molecule is that we have no net polarity, because when one fluorine is pulling the electrons towards itself, the other two electrons on the other side are pulling the electron cloud towards themselves. So this molecule right here has no net dipole. All right, let's take a look at CH2O. CH2O is formaldehyde. And if we were to draw the basic Lewis dot structure for formaldehyde, what we would see is this. But again, we know that we don't have an angle of 180 and two angles of 90 degrees, because this electron group and this group and this group try to get as far apart as possible. And if you have three electron groups around your central atom, which we do with carbon, they're going to push themselves into a trigonal planar situation. So they're going to have bond angles of about 120 degrees all the way around. Now again, when we're looking for molecular polarity, we have to look at our bonds individually and then look at the molecule as a whole. So if we look at the electronegativity difference between carbon and hydrogen, what we saw in one of the previous lectures is that the electronegativity value for carbon was 2.5, and I got that right off of the chart. And the electronegativity value for hydrogen was 2.1, and we had 2.5 minus 2.1 being equal to 0.4. And we said 0.4 still qualified as nonpolar. So neither the carbon nor the hydrogens is pulling the electrons towards itself enough for those bonds to be classified as polar. So we have a couple of nonpolar bonds right here. So we don't draw a dipole moment there. Now we take a look at the carbon-oxygen bond. Oxygen is a lot more electronegative than carbon. So remember, carbon is 2.5, and the electronegativity value of oxygen we can find on the chart. We can see here that it's 3.5, or that's a little bit obscured. Let's see if it's better over here. We have 3.5 right there. So if we go ahead and put 3.5 right there, we can see that the electronegativity of oxygen is a lot greater than the electronegativity of carbon. So what we have is oxygen pulling the electrons towards itself. Now remember, I could draw that dipole moment, that arrow, on the left-hand side of the bond or the right-hand side of the bond. It doesn't really matter. But what we can see from this molecule right here is that there's only one dipole. And we have a shift of the electron cloud in this molecule towards oxygen. So right here, that dipole moment that I drew is just for that single bond. If we want to draw the dipole moment for the entire molecule, what we can do is we can put it on top of the molecule, and we can say that we have the positive end down here, and we put a dashed line through the molecule to tell the person who's looking at this molecule that that is the net dipole moment for the entire molecule. So it goes from the bottom end down here up through the top to oxygen up there. Now the other way we can write that, the net dipole moment for the molecule, is off to the side of the molecule. So let me do a little bit of erasing here. Oops, I erased the carbon. Didn't mean to do that. Let me draw that back in. So we can draw it off to the side, left or right, it doesn't matter. You would do that to indicate that there's a shift in the electron cloud towards the oxygen. The other way we can do it is with the delta symbols. Remember, we don't draw a dipole moment and the delta symbols together. It's one or the other. So let me erase that and let me draw in the delta symbols. So we would say that we have a partial positive down there on that side of the molecule, and up by the oxygen we have a partial negative up there. Okay, so that shows the molecular polarity for that molecule. So let me do a little bit of erasing so I have some room for my BH4. Okay, so not BH4, but CBR4, excuse me on that. Okay, so we have a central atom, carbon, because carbon likes to be central, and if we were to draw the basic Lewis structure for this, it would look like this. All right, but we know that if we were to draw the correct molecular geometry for this molecule, we would not draw a bunch of 90-degree angles. We have a central atom that is bonded to 4 things, so we would have to draw a tetrahedral structure. So we would draw 2 of our bromines along with the carbon in the plane of the screen. So those regular bonds indicate that those are flat. So the BRC and the other BR on the right hand side are flat. Now we're going to have a bromine coming out at us, so we draw the wedge. And we're going to have a bromine going back into the screen, so we will draw a dashed line for that. Now, what are going to be the bond angles on this tetrahedral molecule? 109.5, that's right, because you have a central atom that has 4 bonding electron pairs around it. Now, back to the electronegativity. We said that the electronegativity for carbon is equal to 2.5. The electronegativity for bromine, we go ahead and we look on our chart, and it's got a lot of writing on it, so let's go ahead and erase that. And we can see that on this chart we've got bromine has an electronegativity of 2.8. So we've got 2.8. And if we do the electronegativity difference, what we'll get is a difference of 0.3. Now, does that qualify as a polar bond or a non-polar bond? Well, if you don't remember, let's go back to this slide right here, where we decided that values, electronegativity differences between 0 and 0.4, all the way up to and including 0.4, that is a non-polar bond. So we don't have anybody pulling the electrons towards themselves more than anybody else. So all 4 of these bonds in this molecule are non-polar. Nobody is shifting the electrons towards themselves more than anybody else. So if you don't have any polar bonds in your molecule, can you have molecular polarity? No. So there is no net dipole here. Because you have to have your electrons shifted to somewhere in order for there to be a net dipole or a molecular dipole. All right, let's go on to CHCl3. So I've got a lot of this stuff to erase. Please forgive me. I don't know how to erase the entire slide just yet. I will figure that out soon. Okay, so what we have is a carbon, a hydrogen, and 3 chlorines. Now, if we were to draw the Lewis structure for this, we'd go, okay, I've got carbon, which likes to be central, and then I have hydrogen and 3 chlorines, and all 3 of those like to be terminal. Hydrogen likes to have a single bond and no lone pairs, and chlorines like to have a single bond and 3 lone pairs. And if you need some practice drawing Lewis structures, looking at all your atoms and adding up all your valence electrons, making sure everything has an octet and that you've used the correct number of valence electrons, go ahead and stop here and make sure my structure is correct. It is, but you can go ahead and make sure. What we would see is that we have a central atom that's bonded to 4 things. So we know that if we were to draw the correct molecular geometry on that, we would not have 4 90-degree angles. What we have is we have a central atom that is bonded to that hydrogen and that chlorine, and those 3 atoms are in the plane of the screen, and then we would have another chlorine coming out at us, and the 4th thing that is bonded to that central atom is going back into the screen. Now, if we looked at each of these bonds individually, we'd have to remember the electronegativity of carbon is 2.5, and the electronegativity of hydrogen is 2.1, and the electronegativity of chlorine, we probably would need to look at our chart for that one. And we can see right here that we've got a 3.0. So we can see that our chlorines are a lot more electronegative than our carbons. So those are probably going to be trying to pull the electrons towards themselves. So what we have is this chlorine trying to pull the electrons this way, this chlorine trying to pull the electrons this way, and this chlorine trying to pull the electrons this way. Now the hydrogen is not going to be trying to pull the electrons towards itself in that bond between the hydrogen and the carbon, because hydrogen and carbons have an electronegativity value difference of 0.4, which means that's a nonpolar bond. So each one of those chlorines is pulling a little bit down, because what we will see is this type of structure right here, but we've got chlorines on the end instead of hydrogens. So each one of those chlorines is pulling out and down a little bit. Now, the parts of each of the dipole moments on these bonds that are pulling in the out directions, those are going to counterbalance each other. So when this one pulls out this way, these two over here are pulling out this way and saying, nope, you're not going to shift the electrons to the right, Mr. Chlorine, because we're going to pull back left this way. And the same thing happens for that chlorine and that chlorine. But what they all have in common is that they're all pulling down a little bit. So these bonds, oops, that's probably a bad color to use right there. These bonds right here all have a little component on them where they're pulling in the down direction a little bit. And so those pulls down a little bit by all of those chlorines add up. So the pull out, those balanced each other out, but the pull down is additive. So what we have is in this molecule, you have all of the chlorines pulling the electron cloud in a down direction. So the net dipole for the molecule shows us that this end of the molecule down at the bottom down here is going to be partially negative, which creates a partial positive on the top of the molecule. So again, if we go back to a tetrahedral looking molecule like this, and we have instead chlorines out here, you get this bottom area down here, which has a shift of the electrons that way. So down here on the bottom of the molecule is partially negative, which creates a partially positive region up here at the top of this molecule. Now again, I know that's hard to see on a flat surface, but I will make some videos where we can see the molecules in 3D, and I'll show you this. So you can write the net dipole for this molecule with the little delta symbols like I did here, or we can draw a dipole through the middle of the molecule. So we would do this like that to show that the top of the molecule is partially positive, and the bottom area of the molecule where all those chlorines are pointing down into a little bit is partially negative. We can also draw the dipole moment to the side of the molecule. So we can draw it off to the side on the right hand side, or you could draw it off to the left on the left-hand side like that. But you don't do both, just one or the other to indicate the molecular polarity. Okay, so a question I always get is, where is the dipole pointed if we draw the molecule differently? And that's a really good question. So what happens if we draw this molecule like this? Well, that makes it a little bit more difficult to see, but you would still have the positive region over by the hydrogen, and you would have the electrons being drawn towards the back and to the right. And you could draw it like that. That angle's kind of weird. You could try to make it a little bit better and say it goes like that. But it tends to look best when you draw it like that. So if you were drawing it on the right hand side in the black molecule, what you would probably do is use the delta symbols and say that over by the chlorines we've got a partial negative, and at the hydrogen we've got a partial positive. So wherever we shift the chlorines to, that end of the molecule or that side of the molecule is going to be attracting electrons towards itself, so it's going to be partially negative. And wherever the hydrogen is, that's going to be deficient in electrons, so that's going to end up being partially positive. Okay, on to CH2Cl2. Okay, so we have CH2Cl2, otherwise known as dichloromethane or methylene chloride. Both names are used. Now what we have here is we have a carbon bonded to 2 hydrogens and 2 chlorines. So it looks a whole lot like the molecule that we just drew, except one of the chlorines is replaced by a hydrogen. Now we know that the carbon-hydrogen bonds are nonpolar because the electronegativity difference is 0.4, which qualifies as a nonpolar bond. But we also know that the carbon-chlorine bonds are polar. So what we have is, in this bond, we have a shift out towards the chlorine of the electrons, and over here we have a shift out towards those chlorines. Now what happens is the shift towards this chlorine for the electron cloud that way, and the shift towards that chlorine going that way, those are going to cancel each other out. But what we also have in each of these dipoles is a pull out this way, and those are additive. So what happens is the net dipole for the molecule, we can draw it like this. So we have a positive region of the molecule over by the hydrogens, and we have a partially negative region over by the chlorines. The other way that we can indicate this is with the delta symbols. So we would do partially positive side, and we'd say that, oops, that's a negative. And we would say that this region over here is partially negative. So this zone over here is partially negative, and this zone over here is partially positive. We can also draw the net dipole for this molecule off to the side, and what you would do is point it like that. You can draw it up there, or you could draw it up there. Either way, you just don't want to do both. You do one or the other, and again, you don't write the dipole moment and draw the delta symbols. You do one or the other. Now, the question is, what happens if you draw the molecule in a different way? Which, again, is a good question. And what we'll see is that if you draw it a different way, the dipole moment will still be headed towards the chlorines. So the arrow won't point the same direction, but it will point towards the chlorines. So we would do this like this, indicating that the electron cloud is being pushed over towards the chlorines, and we've got a partially negative side of our molecule and a partially positive end of our molecule. So again, either the dipole moment or the delta symbols. So over on this side of the molecule is partially positive, and over on this side of the molecule is partially negative. You could draw it either way. And obviously there are different ways to draw it other than the two ways that I drew it. But the arrow will always be pointed between the two chlorines, and the plus symbol will always end up between the two hydrogens. And that, my friends, is the end of chapter 4. Yay!